Alright, ladies, so let's go ahead and take a look at our good old friend, position, velocity, and acceleration. And just to remind you, let's use x of t right now. X of t is our position, right? Anytime I took the derivative of x of t, we called it the v of t, oops, also known as our velocity. And we also knew that if we took the second derivative, which was the derivative of the velocity, that gave us our acceleration. So, acceleration. Thinking for spell check. So, what we know is if I can take these derivatives, I can take the integrals. So, the integral of acceleration has to equal the velocity, and the integral of velocity has to equal the position. So we're going to use these two concepts to find out how we can use a fundamental theorem to solve such problems. And we'll relate it to some real-world problems as well. So if I read this problem here, it says a particle moves along the y-axis with the velocity given by v of t equals 3t squared plus 8t, and time has to be greater than or equal to 0. If the particle is at position y is equal to 5 at time t equals 2, what is the position of the particle at time t equals 4? So what we see is we do have a derivative or a velocity, right? So velocity is a derivative of the position. We have an initial condition of y of 2 has to equal 5. And we have an endpoint of t is equal to 4. So in order to find y of 4, we must take our initial condition, y of 2, and add our change, which is going to be from 2 to 4 of our velocity. So 3t squared plus 8t dt, since I'm now in functions of t. And if we plug in y of 2 is equal to 5 plus this integral gives us 3t to the third over 3, which is t cubed, plus 8t squared over 2, which gives us plus 4t squared. And then I must plug in 4 and 2. So now I just use a fundamental theorem of calculus to solve this, and I get 5 plus parentheses 4 to the third is 64 minus 4 times t squared, which is also 64, minus, when we plug in 2, we get 8. 4 times 2 squared is 4 times 4, which is equal to 16. And so now we get 5 plus 128, and we get, let's see, that's equal to 24 minus 24. And so we get 133 minus 24, which is going to give us 109. So the position at time t equals 4 is 109 units. So let's go ahead and take a look at another problem. And this one says a particle moves along the x-axis, so at any time t greater than 0, its acceleration is given by the following function. If the velocity of the particle is 6 at the time t equals 0, what's the velocity of the particle? Well, we see that we have our initial condition right here. The velocity at time is equal to 0 is equal to 6. Our end value is t is equal to 3, and we see our derivative is a of t. Well, this works out perfectly because we know that the integral of acceleration is velocity. So what we're going to see is the initial function v of 0 plus the integral of acceleration, which goes from 0 to 3. Plug this in, and I get sine of pi t over 4 dt. And we do a basic integral. V of 0 is equal to 6. Plus, if I do u substitution, I notice I have to pull this reciprocal out. 4 over pi. The integral of sine is negative cosine of pi t over 4. And then I plug in 3 and 0. And if we continue with this, what we see is we get 6 plus 4 over pi, parentheses, negative cosine 3 pi over 4 minus, which becomes a plus, cosine of 0. And if we plug this in, we get 6 plus 4 over pi times negative cosine of 3 pi over 4 is equal to radical 2 over 2. Cosine of 0 is equal to 1. So plus 1. And so if I wanted to simplify this out, what we see is we get 6 plus, this 4 cancels this to get 2 radical 2. And this becomes plus 4 divided by pi. Good. So let's take a look at a few other problems and see how this can be used to solve different word problems. This says if g of x is an antiderivative for f of x, so that means f of x is the same as g prime of x, and g of 3 is equal to negative 5, write but do not evaluate an expression involving an integral that represents g of 7. So what we see is g of 7 is our endpoint. Has to equal our initial condition, g of 3 plus the integral of our initial condition of 3 to our endpoint of 7, g prime of x dx. And if we plugged everything in, we know g of 3 is equal to negative 5 plus g prime is the same as f of x, so we can just rewrite this as 3/7 f of x dx. And it says do not evaluate, so we can stop right here. Good. And so we have a couple more problems, and it says the rate of change of the altitude of a hot air balloon is given by this. So since it says rate, we know that this right here is a derivative, right? Anytime I see the word rate, I know we're a derivative. From 0 to 7, it says determine when the altitude is decreasing. So we know something is decreasing when we set the derivative equal to 0. According to the sentence, we already have the derivative, so what we need to do is set our derivative r of t equal to 0. So that means t squared minus 4t plus 3 is equal to 0. And from here, we know that we need to factor. And we see that t is equal to 3 and t is equal to 1. Well, to find out if I'm increasing or decreasing, I need to do my number line. And so I'm going to bring out our handy dandy number line. And if we mark this as 1 and this as 3, we can go from 0 to 7. So let's just pick 0, 2, and 4. Scroll up just a little bit. If I plug in 0, I notice that I get negative and negative, which means we have positive values right here. If I plug in 2, we notice the first part is negative, but the second part is positive, which will give us negatives in this region. And if I plug in 4, I notice I get 2 positives, which is going to give us positives right here. So we are decreasing from 1 to 3. So the question is asking, I want to know the change in altitude. So in order to do that, I need to take an integral. Since I'm looking for a change, I know my change goes from 1 to 3 of the derivative, which was t squared minus 4t plus 3 dt. So I solve this and I get t cubed over 3 minus 4t squared over 2, which is 2t plus 3t, and then I plug in my 3 and my 1. And if I continue with this algebra, we get 3 to the third is 27 divided by 3 is 9 minus 6 plus 9 minus everything when I plug in 1, which is 1/3 minus 2 plus 3. We notice we have 18 minus 6 is 12. On here we get minus 1/3. Negative 2 plus 3 is 1, so that's minus 1. Oh, I'm sorry. I think I made a calculation error here. There was a squared right here. Yeah, sorry, that's 2t squared. So that's 2 times 9 is 18. So this should actually say minus 18. And that means this cancels this. So I apologize for that. But all of these cancel. Then we get negative 1/3 minus 1, which is the same as negative 4/3 meter. So what we see is this hot air balloon from the time 1, 3, it's not going up, it's actually decreasing and going down negative 4/3 meters. Alright, so let's take a look at the last problem. It says a pizza is heated to a temperature of 400 degrees Fahrenheit. Okay. It's taken out of an oven and placed in a room that's 75 degrees at T is equal to 0. The temperature of the pizza is changing at a rate, so we have a derivative right here, negative 3 radical T. To the nearest degree, what's the temperature at T is equal to 4? So what we do know is, in order to find the temperature at 4, I need my initial condition, which was when the temperature at 0, plus I need to integrate from 0 to 4 my rate, which is negative 3 radical T dt. So then I got to figure out, what is the initial condition? What was the temperature of the pizza when I pulled it out? So I have two numbers. I can pick the 400 degrees or the 75 degrees. Well, we're looking at the temperature of the pizza. So at 0 minutes, the temperature of the pizza right when it came out of the oven was 400 degrees. So this is equal to 400 plus, I'm going to pull out that negative 3. T to the radical T is the same as T to the 1/2, which if I add 1 is 3/2. I multiply by the reciprocal, 2 over 3, plug in 4 and 0. Well, what you notice is if I plug in 0, I get 0. These 3's cancel, and what I actually get is 400 minus 2 square root of 4 to the 3rd. Like I said, if I plug in that 0, it's going to cancel anyway, so we can just do that from there. And what we see is we get 400 minus 2. Square root of 4 is 2 to the third, which gives us 400. This is the same as 2 to the fourth, which is 16. So the temperature of the pizza is actually 384 degrees Fahrenheit after the first 4 minutes, which is still pretty hot, which means you probably shouldn't eat it just yet. So this is a couple ideas of how we can do this. You can see this problem right here can be done for cooking and chefs, making sure that you don't serve your food too hot. The previous problem is for safety, making sure we know where our hot air balloon is going to be going if we want to take people out on a ride and so forth. So, it seems like a stretch, but these are some ways that we do the fundamental theorem of calculus in real world. Thank you.